Hello everyone, welcome again to our YouTube channel Engineers World. So today is the third lecture of RCC and today we'll start our lecture with Young's modulus. Young's modulus of concrete. So before studying the Young's modulus of concrete, we must first know what is Young's modulus. To understand this, if we simply draw a stress strain curve of any material, if this is stress and this is strain, and up to elastic limit, for example this is point O, and let this be the elastic limit point. This may be some angle theta. So we know that slope of this angle will be tan theta, and tan theta will be equal to some value of stress upon some value of strain. And this ratio of stress and strain is Young's modulus. So this was a simple definition of Young's modulus. So in terms of concrete, the Young's modulus of elasticity is the ratio of axial stress to the axial strain under uniaxial loading within the linear elastic range. For concrete under uniaxial compression, this is valid only in the very initial portion of the stress strain curve. Very initial portion of the stress strain curve, which is nearly linear. That is, load is of low intensity and of short duration. Load is of low intensity and of short duration. So sustained loading introduces the effect of creep. Now what is creep we will discuss in this video further. Now to understand the Young's modulus of concrete, we'll first make the stress strain curve of concrete. So if I talk about the stress strain curve of concrete, it is somewhat like this. It's somewhat like this. This axis shows stress and this shows strain. Now see, there are a lot of various types of Young's modulus of concrete basically. See, first of all, the Young's modulus of concrete is denoted by ESE. Now as per this stress strain curve, the first thing is initial tangent modulus of concrete. The first type of Young's modulus of concrete is initial tangent modulus of elasticity. It is simply the slope of stress strain curve of concrete at the origin. So at the origin, whatever the slope is, that will be called as initial tangent modulus of elasticity, represented by EIT. Initial tangent modulus of elasticity of concrete. Now second comes tangent modulus of elasticity. So what is tangent modulus of elasticity? The slope of tangent at any point on the curve is called tangent modulus. For example, this is a point and I'll make a tangent. The slope here will represent the tangent modulus of elasticity. So at any point on the curve, the tangent, the slope of tangent with that it makes with the horizontal will be called as tangent modulus. Now the third term comes as, or third type of Young's modulus comes as secant modulus of elasticity. So what is secant modulus? It is the slope of the line joining any point on the stress strain curve to the origin. So for example, I'll take the same point and I'll join it with the origin like this. Let this point be the P, and I have joined it with the origin O. Now this slope will be called as secant modulus of elasticity, represented by ES. Secant modulus. So this was all about different types of modulus of Young's modulus of concrete as per the stress strain curve of the concrete. Now we will move on to the next topic, that is creep. You all might have heard about creep. So what creep is? Creep is nothing but it is defined as plastic deformation under constant load or stress. So creep can be simply called as plastic deformation under constant load or stress. So concrete under the action of constant load or stress continues to deform with time. This plastic deformation grows rapidly and reaches highest intensity in the first 3 to 4 months after application of the load, and then continues to increase gradually, approaching the limiting value in the period of around 5 years. So if I make the typical creep time curve, it is just like this. This shows time and this axis shows deformation. So initially the curve goes like this. So initially it grows, plastic deformation grows rapidly and reaches highest intensity in the first 3 to 4 months after the application of load, and then continues to increase gradually, approaching the limiting value in the period of 5 years. Since the creep increases at a faster rate in the early ages, the erection of walls on newly formed concrete should be prolonged. Otherwise, cracks develop in walls after a period of 6 to 12 months. So, if I complete this graph, it will show like this. It will be just like this. Now, why is there sudden drop in this curve? I'll explain briefly. See, this portion is called as permanent deformation. This is the specimen under sustained loading. Specimen under sustained loading or creep. And this time shows the load, removal of load, when load is being removed. See what happens at any time when the load is removed, the elastic recovery first of all takes place. So this portion may be called as elastic recovery. This is called elastic recovery. So at any time when the load is removed, the elastic recovery takes place immediately. while part of the creep deformation recovers at a slower rate, leaving permanent deformation logged inside. So after elastic recovery, there is creep recovery. So this portion is called creep recovery. And after creep recovery, there will be no recovery at all, and this portion will be called as plastic deformation. Now see, this whole area may be called as creep. From there to this, at the starting point, this is called as creep. And this portion is elastic deformation. So this was the relationship between, or you can say variation of creep deformation with time. Now we'll further move on to, see, there are two types of models of elasticity of concrete. One is called as short term and another is called as long term. Now first is short term. Short term modulus of concrete. So what do you mean by short term? See, I recently discussed about secant modulus. So this is another name of secant modulus, you can say. Secant modulus. So in this type of modulus of concrete, no effect of creep is being taken. So you can write it as E short. So as per IS 456 2000, it defines the value of short-term modulus of concrete as 5000 root of FCK, where FCK is the characteristic strength of concrete. So this was all about short-term modulus. Now moving on to next type, that is long-term. Long-term modulus of elasticity of concrete. Simply represented by E long. So when we take the effect of creep, then it is called as long-term modulus. So the formula as per IS 456 is E short term upon 1 plus theta, where theta is called as creep coefficient. See, upon substituting the value of E short term, we will get 5000 root FCK upon 1 plus theta. So this will be the final value of long-term modulus of elasticity. See, this creep coefficient is very important. As per IS 456, the value of creep coefficient decreases with the age of loading, and this decrease has been shown in a table which I'll be drawing. See, as per 456, there has been given a table in which here is age of loading, the specimen, and this shows creep coefficient, that is theta. So at 7 days loading, creep coefficient was found to be 2.2. This is as per IS 456 2000. Secondly, for 28 days the value of creep coefficient is found to be 1.6, and after 1 year of loading, its value is 1.1. So the main thing to be noted here is that the value of creep coefficient goes on decreasing with the age of loading. So now our next topic is properties of reinforcement and its use in the reinforced concrete structures. So the reinforcing steel is classified according to the yield strength of the steel that is to be used in construction for structural purposes. The specified yield strength is called as grade of steel. So, properties of reinforcement. So here we are concerned with the grade of steel. So what is this? The grade of steel represents the yield strength of steel. So different grades of steel are found, like Fe 250, Fe 415, Fe 500, and so on. See, just like in concrete, there were different grades like M20, M25, where M represented mix. So here also there are different grades of steel like Fe 250, Fe 415, Fe 500, where these numerical values represent their characteristic strength, or you can say specific yield strength. See, now we will study a little bit about these different types of reinforcing steel. I'll just explain it with the stress strain curve of 3 different types of reinforcing steel. See, the first one is, you all know it very well, that is mild steel, also called as Fe 250. Remember, Fe 250 is called as mild steel. This is stress versus strain curve. Now our next is Fe 415. So its curve is somewhat like this. This is for Fe 415 grade steel. And next one is Fe 500. So these are the different stress strain curves for different grades of steel. You all might be familiar with this type of mild steel curve, but these are new for you. So what is mild steel? It can either be mild steel. It can either be ordinary or hot rolled with characteristic strength of 250 Newton per mm square. This is characteristic strength, Fy, you can say. Now there are some one is cold twisted bar. Cold twisted bar. These are HYSD and these are of grade 415, HYSD. The full form of HYSD is high yield strength deformed bars. So these are also used as reinforcement. Third one is TMT bars, thermomechanically treated. And these bars come in the category of Fe 500. See, the important point to be noted about TMT bars is that their outer shell has very high tensile strength, but inner core is soft and ductile. See, if this is TMT bar, cross section of TMT bar, the inner core is very soft, you can say. Inner core is soft and ductile. Whereas the outer covering, his outer shell has very high tensile strength. This outer shell. has high tensile strength. So this was all about properties of reinforcement and different types of reinforcing steel. Now you might remember this portion. This portion is called as yield plateau. If I consider only the stress strain curve of mild steel, so this region is called as yield plateau, where yielding takes place. Now see, here are two important concepts. One is cold working and another is hot rolled. So what happens in case of cold working? Steel reinforcement is stressed beyond the yield plateau. When steel reinforcement is stressed beyond this yield plateau, then this can be done either by stretching or by twisting, and then it is unloaded. This process is called as cold working. Cold working. So what is cold working? When the steel reinforcement is stressed beyond the yield plateau, and then which can be done either by stretching or by twisting, and then it is unloaded. It's called as cold working. And what about hot rolled reinforcement or hot working? You can say hot mold. So in case of hot rolled mild reinforcement, you can say hot rolled mild reinforcement. So this process was cold working, and the bars were called as cold twisted bars. And another is hot rolled mild reinforcement. So in case of hot rolled mild reinforcement, a yield plateau is observed at upper yield point, resulting in large deformation in steel and further resulting in large cracking of structure. So this was all about cold working and about hot rolled steel reinforcement. Now next we will discuss about the stress strain curve for cold worked HYSD bars. Stress strain curve for cold work. Cold worked, which means high yield strength deformed bars. And what is the grade for this? Its grade is FE415 and FE500 also, and also FE500. So the stress strain curve comes out to be like this. So this axis shows your stress and this axis shows your strain. So this is the stress strain relationship for cold worked HYSD bars. As cold worked bars do not show a definite yield point, the characteristic strength or yield stress refers to a conventional value of 0.2% of proof stress. 0.2% of proof stress. So the corresponding strain will be 0.00. 0.2% of proof strain. 0.002. 0.02 means 0.002. If this is 0, this is 0.001. So we will consider yield at corresponding to this point. See, actually these bars were subjected to tension test. So this was all about the stress-strain relationship of HYSD bars. Now the next topic that we will start is working stress method. These are basically design methods based on experimental investigations. So among these methods, we are starting with working stress method. There are also other methods like limit state method. So we will start with working stress. So what do we mean by working stress method? See, in this method, we assume that the concrete and steel behave elastically. Both concrete and steel behave elastically. They behave elastically. Moreover, the reinforced concrete member is designed using classical elastic theory such that the stresses in the material resulting from the worst combinations of working loads do not exceed the allowable stresses. So here we keep in mind that the stresses in the material resulting from the worst combination of working loads do not exceed the allowable stresses. So we are concerned with working loads. Moreover, the allowable stresses or permissible stresses are then obtained by dividing the limiting stress of material by a factor of safety. So IS 456 provides a factor of safety against attainment of upper limiting stresses such as ultimate compressive stress for concrete and yield stress for steel. Which we will discuss in further lectures. Now we will discuss some permissible stresses in working stress method. Permissible stresses. Among these, the first one is direct compression. Direct compression. So this type of stress is represented as sigma cc. So to demonstrate this, or in order to understand this, if this is a body and it is subjected to compressive forces, or you can say direct compression by a load of P. So if I take a cross-sectional area here, somewhat here, because the stress distribution here in this portion will not be uniform. It will be more in this zone and less in this zone. So we will take the section at some distance from this, so that we will get uniform stress. So if this is the cross section of this member, so if I make the stress diagram, this will be the stress diagram. Stress is simply force upon cross-sectional area. So this will be in direct compression. So here compression I have represented with positive sign. So the next is direct tension. The next permissible stress is direct tension, represented by sigma, you can say T. So if this is an element or a member and it is subjected to a tensile force P, and the deformed shape will be somewhat like this. So this is the cross section and this will be its stress diagram of direct compression. I have denoted it with negative. Sorry, direct tension. So this was all about direct tension. Now these were direct stresses, direct tension and direct compression. Now the next one is bending stress. Bending stresses. See, these will have combined effect of bending compression as well as bending tension. It is represented as sigma C BC. So if I make a beam here, suppose this is a beam and it is subjected to some loading. These are the supports. If I make its deflected shape, it will be just like this. You can see the bottommost fiber is in tension and topmost fiber will be in compression. So if I take this section of the beam, A dash, B dash, and the corresponding section in the deformed beam, we'll see that the shape will be like this in this section. This will be A double dash, A triple dash, B double dash, B triple dash. And this portion will be in tension and this will be in compression. And also if I make here the bending moment diagram of this beam, it will be somewhat like this, with maximum bending moment at the center. So this was the simple demonstration of a simply supported beam subjected to a UDL and its deflected shape and the bending moment diagram. Now the section that we have chosen, we will study the whole cross section now. Now see, if I'll take the cross section of the beam, here is the cross section and these are the reinforcements. This is our neutral axis. So if I make the bending stress diagram, it will be just like this, where these are tensile stresses and this above the neutral axis are compressive stresses. Compressive stress. Tensile is denoted by negative and compressive by positive. So this was the bending stress diagram of the cross section of a beam subjected to some general loading or UDL. Now how does this triangular stress diagram came for a beam subjected to bending? So I'll try to visualize it. Now you just remember this type of diagram. Now we will work on it. See, if I'll make the beam in 3D like this. So this is the 3D view of the whole beam. If this is our neutral axis, I'll make the neutral axis. This is our neutral axis. Now we know the topmost fiber is subjected to compression and the bottommost fiber is subjected to compression, and at neutral axis the bending stresses are 0. That means bending stresses are increasing linearly from neutral axis to the extrememost fiber. So if we take the firstmost fiber, topmost, it will be just like this. Compression. It is just a visualization how this bending stress diagram came into existence. So this is, you can see, compression. This is O point. Now coming to the tension zone. Again, the diagram will be like this, and here it will be like this. It is also a neutral axis. It will touch like this. So this is clearly a visualization of bending stresses. See, bending stresses are always acting in longitudinal direction, remember, and perpendicular to the cross section of beam. These bending stresses are acting in a longitudinal direction. See, if this is the length of beam L, these stresses are acting in along the longitudinal direction and perpendicular to the cross section of the beam, and they are acting across this section. That means perpendicular to the cross section of the beam. So this was all about various types of permissible stresses in working stress and a brief introduction of working stress method. This was all about today's lecture. In the next lecture we will study in detail about the working stress method and analysis using working stress method, and also design of beams using working stress method. So hope you would have liked today's lecture. Goodbye.